From the beautiful North Studios of Way Happy, this is Mr. Meyer and section P3 functions and their graphs. All right, so we're going to talk about function notation, which is the first part, then domain and range, then sketching, then identifying different transformations, and then lastly, classifying. So a lot of little business here to do, but mostly, again, stuff you've seen. So let's start off with function notation. Remember that you could write an equation as y equals whatever. And in this case, y equals x squared plus 7. And I can then say, well, it's a function because it passes, if you graph it, it passes the vertical line test. That's how I check to see if it's a function. And it passes the vertical line test. So I can call it a function. And then what I can do is say this function, when evaluated with an x in it, that's what those parentheses mean. The function, when you evaluate it with a letter x in it, it would look like x squared plus 7, right? And then I ask you different questions like I do down below, like what's f of 3 of a? So that means what would the function look like if you evaluated it with a 3a in its place? Well, we know that f of whatever is equal to whatever squared plus 7, right? Because it was f of x is equal to x squared plus 7. So f of whatever is equal to whatever squared plus 7. Now I'm going to go ahead and do what you wanted me to do. You want me to do a 3a. So f of 3a is equal to 3a squared plus 7. And now be careful with the parentheses there. It's kind of important that you simplify this correctly and you get this down to, what is that, 9a squared plus 7? And you're like, yay, there's the function evaluated with a 3a in its place. So in other words, I took the x out, I put a 3a in its place. Let's make it a little scarier, right? Let's put a b minus 1 in there for you. So again, f of whatever is equal to whatever squared plus 7. So in this case, we're going to say, all right, the whatever is a b minus 1 this time. And if I evaluate that, I get f of b minus 1 is equal to, foiling, right? That's b squared minus 2b's plus a 2 plus a 7. And so f of b minus 1, if we clean that up, is b squared minus 2b plus 9. And we have it evaluated. Beauty. All right, well, let's make it even more gross. Look at that and see. Now, that's something we're going to do with derivatives. And then you're going to be like, wow, that's great. Thanks for that. But we're going to show you shortcuts and other cool things to do with it. But for right now, let's talk about how you read this, right? So it's the function of x plus delta x minus the function of x all over delta x. What the heck? I don't know what that means, but I know I can do it. Because what is that? That is the function with this whatever, right? Well, I'm not even going to write the left side because the left side's there. And so I'm just going to ignore that for a second. And I'm going to say, all right, what is it? It's whatever you want squared plus 7 minus f of x would be whatever squared plus 7 all over delta x. And you're like, good luck. I have no idea. But what am I plugging in? In the first one, we're plugging in x plus delta x. So x plus delta x. And in the second one, I'm only evaluating it for an x. All right. Evaluate for an x. Piece of cake. All right. Now let me see what the heck you got. Okay. Foiling this out, I would have x squared plus 2 delta x's. No, sorry, x delta x. So I guess I'll do x delta x. And then plus delta x squared plus 7. And then distribute the negative minus x squared minus 7 all over delta x. Oh my goodness. So let's see if anything canceled out. Oh, thank goodness. X squared and x squared canceled out. 7 and 7 canceled out. So all I'm left with is 2x delta x plus delta x squared all over delta x. Well, that kind of looks like the delta x's could somehow cancel in there, right? So let's do it carefully. I'll factor a delta x out of the top, and you would be left with 2x plus delta x all over delta x. Yep. And look at that. Boom and boom, cancel, because it's a multiplier, not an adder, right? We don't want to do that. And you would be left with 2x plus delta x. Boom. That is equal to that. Crazy, but it was function notation. They tried to scare us. You've been doing this for a long time. You've done it with numbers, and then we would do it with a letter, and then we'd number in a letter, and then added involved foiling, and then oh my gosh, this complete master mess. But look at how simple it turned out. It did make me feel, a little better. Let's maybe throw one more thing, and that very important star thing is the thing I want to make sure I mention. Domain and range of a function. Domain, you can tell me domain easily, right? By looking at a graph or not looking at a graph. There's 3 algebraic rules that you can never, ever forget, right? They have the star. And the things are that you can have no zeros in denominators. That's rule number one. You can't have that. No zeros in denominators. That doesn't exist for the x's. So it can't happen. So it won't be in part of your graph. No negatives under square roots. It just doesn't make sense. Now, again, odd roots you can have negatives under. But even roots, second root or fourth root or sixth root, no negatives under there. Can't happen. So rule number 2 is don't let negatives happen under there. It won't be part of your domain. The x values won't be allowed. And last but not least, the one that people forget because they're scared of logs is no zeros or negatives after the word log, right? So whatever the log base is, I don't care, but don't let me have negatives or zeros after the word log. Those are our 3 different domain rules, right? And that's the stuff we want to talk about. Now, people can give you an explicit domain where they say, hey, will you graph this equation right here, 1 over x squared minus 4, but only to show me the graph for these x's. That's it. From 4 to 5, that's all I want to see, nowhere else on the graph. And you're like, oh, all right. Desmos really good at that. And so you would. That's called an explicit domain. An implicit domain is when I don't tell you anything, or an implied domain, I don't tell you anything. I'm just like, here, graph this, right? And you worry about the domain. So like the second one that says graph this, and then you tell me what isn't allowed. And again, no zeros in denominators, so that's going to be not allowed. All right, what's example 2? The domain of the function is all sets of values greater than 0. We know that. Find the range. Okay, so what is the range? So again, I like to think of these as graphs. When I do domain and range, I will kind of think of the graph. So what is this? A square root graph, which I call a shooting star. And it's shifted right 1 unit. So I go right 1, and I draw my shooting star graph, which looks like this. Boom, right? All right, you can see the domain is everything bigger than 1, which is what they said here. And that makes sense because all the x values are bigger than 1. What about the y values? And how do I figure that out if I'm just looking at a graph? If I want to find the domain real quick, I smush the graph onto the x-axis. I pull all these points down to the x-axis. Every single one of these points, I smush them down here, and I look at the x-axis now as a number line. And I say, oh, that domain was the number line that's filled in is all the way from 1, and it goes on forever and ever. And I do the same thing with range. With range, I take the graph and I smush it onto the y-axis. So wherever there's graph, I would smush it onto the y-axis, and you would see graph here, right? You wouldn't see any down here in the negative region because there's no graph there. And so when you squish it on the y-axis, it wouldn't be there. So the range is everything from 0 up. So the range is everything from 0 all the way to infinity. All right, let me ask you a few questions, and I will be right back. Excellent work. All right, what about sketching a function? Now, let's go ahead and sketch the next couple graphs. There's about, when you sketch a graph, you plot points, right? And that's what that little thing at the top there is saying. You're just saying, hey, look, you do the distance from the y-axis, we call that x. You call the distance from the x-axis, we call that y. And we plot those points over and over and over again. Now, there are some functions that you should know how to sketch. I have 8 here that I clipped from the book, and I almost feel like there should be some more. But these are 8 very familiar ones, like linear functions, or what they call the identity function, right? It should be a line. 2 points should make a line. You need 3 points to make a parabola. You should know what the squaring functions look like, that they make a parabola, right? You should know cubic and there's some little tricks you should know for each one, like on a line, I usually know the y-intercept and the slope is something I know. A parabola, I usually know the vertex, and then I know that I can go, on either side, 1 unit out and 1 unit up, and I can plot those points. That'll help me, and then I can go out 2 units and up 4. That'll help me plot graphs, and when I translate stuff. The cubic function, I usually know the vertex, and you go right 1 and up 1, and left 1 and down 1. Now, that's very generic. It has to be a nice, clean cubic function, but that's something you can always plot. Square root function, right, is something that I know where it starts, and then if you go right 1 and up 1, because the square root of 1 is 1, or the square root of 4 is 2. So I kind of know those couple points that I can always plot on graphs. Absolute value, same kind of thing, it just goes up to the right 1 and up to the left 1, and you make a V shape. The inverse function, the 1 over x function, that one I like to know the asymptotes, right? It's got an asymptote at x equals 0. It's got a horizontal asymptote at y equals 0, and then it lives between those. It wants to be on the horizontal, but then it freaks out because the vertical asymptote. And then sine and cosine, make sure you know which one starts at the origin and which one starts at an amplitude. And there's 8 basic functions that you should be able to sketch kind of quickly and not be too scared about. What about transformations? That's really key in almost every class you've ever done, right? Where transformations are, if you are added or subtracted, that's going to slide it left and right and up and down. Remember, if it's happening to just the x, then that you're going to do the opposite of it. So what feels like a plus would actually be a minus. It would be to the left, and whatever feels like a minus would be a plus actually to the right. So you can see that right here, right? How they move right and left. They do the opposite of what you would expect. If you add or subtract the whole entire function, right, to the x squared graph or the sine graph or the rational function, whatever, whichever function you take it and you add something to it or subtract something to it, that's going to move it up and down, and that's normal. That's like if it's negative, it's down, because it's on the outside. It's normal. Everything on the inside is weird, right? If you put a negative out front, flips it over the x-axis. If you put a negative on the inside, flips it over the y-axis. Multipliers, which I don't know why I don't have any multipliers on here. If you multiply anything greater than zero, anything bigger than one, that's going to be a stretch. If you multiply something between 0 and 1, a fraction that is smaller than 1, you're going to have a shrink. Unless it's on the inside, then it's the opposite. On the outside, we talk vertically, stretch and compress. On the inside, we talk horizontally, stretch and compress. So a lot of different things, and every function can be written in that form. So kind of here, I said example 3, suppose you have a function. What does a, b, c, and d do? So again, let's start with the easy one. C, since it's minus c, that would move it left or right. Left or right. Oops, I don't know how to spell right. D moves it up and down, right? And then we have multipliers here. There's 2 types of multipliers. This one is a vertical multiplier. So this would be a vertical stretch or shrink. Again, since it's on the outside, it's normal. It's going to be, if you multiply by a number bigger than 1, it's a stretch. If you multiply by a number smaller than 1, it's a shrink. It compresses it vertically. Where this guy's on the inside with the x. He's on the inside on there. And you know what? I should have had the function there, notation. I should have had f right here to tell you it's still the function. But there, B is on the inside happening with the X. So there'd be this little extra F there. The B is happening on the inside, so it's the opposite, but that's in the horizontal direction. So, and since it's inside, it's opposite. So if it's bigger than 1, it's a shrink actually. And if it's smaller than 1, it's a stretch. So there are all the different things that could happen to you when you have these kind of transformations. And lastly, let's talk about classifications and combinations of functions. Now, classifications, that's just like, what a linear function is, x to the first. You know that x squared is a quadratic. You know x cubed is a cubic. You know what a monomial is because it's got one term. If it has 2 terms, we call it a binomial. If it's got 3 terms, we call it a trinomial, right? So just that little vocab stuff like that. And one thing that I think is super important is that what the end behavior is of graphs. And that's what I tell you here. The leading coefficient tells you what the right side of a graph does. If the leading coefficient is positive, then I know that the right side of the graph goes up. And if it's negative, I know the right side goes down. So if somebody gives me an equation, like let's do a parabola, you know what a parabola looks like. Say it's negative 7x squared, right? That leading coefficient is negative. That means the right side goes down. That means the graph on the right is going to be going down like that because it's a parabola. Well, it's a parabola. And so I'm like, the leading coefficient will always tell you. So even if that was x cubed or x to the 4th or x to the 5th or x to the 100th, because of the negative 7, I know the right side goes down eventually. Then the degree tells you what the left side of the graph does. So the degree, if it's even, then it copies, I would say what? The left copies the right side. And if it's odd, then I say the left side does the opposite of the right side. And so since this is even, then I just say, oh, the left side does what the right side did. It also goes down. Now, it doesn't tell you what's going on in the middle. There's a lot of twists and turns and changes of directions in there, little bumps. But it does tell you the ends, which side's going up and which side's going down, or if they're both going down or they're both going up. Super nice to know. So that's why I wanted to share it. Then what do we talk about? Combination of functions. You can add functions together. You see there. You can subtract. You can multiply. You can divide. and really you're just combining like terms. Just make sure you pay attention to the symbol in between, like adding, you add the two together, and multiplying, you multiply. So like on this one, I would actually FOIL, right? But this one, I would just combine like terms, which doesn't look like they have any like terms to combine. So except for the 3 and the 1. So be careful that you pay attention to the symbol in between. And then last but not least, probably the hardest one I think in functions is doing the what we call the composition of functions, where you plug one function into the other. And we already did that earlier, right? Like if you see a fog problem, then there's f and there's g. And what I do is I go, all right, that's just really f of g of x. It goes like this. And then I can take out g of x and put in what it is. It's cosine x. So what does this mean? This means go to equation f. Remember what we do? I go like, it's like 2 and then whatever minus 3. And whatever that whatever is, that's what I'm going to substitute in. So it's cosine. So this would be 2 cosine x minus 3. And you're like, yay, there is your f of g of x, right? That's your f of g problem of x. All right, how do you do g of f of x? Well, that's the same kind of, there should be an x here. That's the same thing as g of f of x. So what does that mean? That means g of whatever f of x is, 2x minus 3. So go over to g, which is cosine of something, and take that something out and put in 2x minus 3. And there is your GOF. That's it. Have a good day. I'll ask you some questions. I'll see you tomorrow. Stay happy.